Hello! Last episode, while looking how to build an AND gate, we found a solution using diodes, but we weren't impressed. The gate was really nitpicky about its inputs, and the signal degraded if you change one gate after another. Today I want to discuss the obvious choice for AND gates, transistors. After all, who hasn't heard that we live in the transistor era and that modern electronics is all made of transistors? Surely the solution to my problem must be here. I didn't have much detailed knowledge of transistors, except having heard that they were like electronic switches and as analog amplifiers, although analog amplification is not something I care much about in a digital circuit. I had some in my electronics kit labeled 2N2222A. And from very brief research, I found out that these were NPN bipolar-junction transistors. Fancy. But the important thing seems to be that they have 3 pins, one of them controlling current flow between the others. According to the internet, the base, which is the middle pin in my transistor model, is the control of the switch. When you have a current there, current can flow from the input called collector to the output called emitter, like a closed switch. When you don't, it's like an open switch. With that mental model, I took my circuit based on switches and decided to replace the switches by transistors. In addition to that, I saw that everybody puts a resistor in the base of the transistor, which makes sense. The base probably doesn't need a huge current to activate the flow from collector to the emitter, and I'd rather not put too much current and damage the transistor. Let's try a 1000 ohm resistor. And finally, the gate output by itself shouldn't be floating when both transistors are off, so I will add this pull down here. Let's make it, let's say, another 1000 ohms. The idea here is that if both are active, these two paths will allow 5 volts to flow into the output and, in this case, turn on my LED. Otherwise, if any of these are off, then this point in the circuit will be grounded and will be around 0 volts. Okay, let's give this a try. I will start with this slightly improved input. I've got these single pole double throw switches here that never leave a floating output, so I don't need pull-ups or pull-downs. This will get rid of some of the issues we had in the last video. Now I can flip these switches and power a LED and measure clean 5 volts and 0 volts straight into one of the two rails. It's time to build our gate. I have put the breadboard in this direction so the build looks more similar to the diagram. I'll put the transistors first. It's quite important to get the pinout right, not every transistor uses the same. Also, if you're doing this yourself and not using a 2N2222, you should ensure that it's at least NPN. Let's add the wiring and the resistors connecting to the inputs. Down here I have an output LED with a 330 ohm resistor, and I can plug this to the gate output. Okay, let's test this. Let's turn everything off. Output is low. If one output is high or the other one, the output is low. And if both are on, this doesn't work? Okay, so I made a mistake. I had plugged the LED the wrong way. Now we have high inputs with high output. In this case, output is low, this one too, and this last case, low output as expected. Let's measure the actual output of the gate. If I measure here, we can see that we actually have a significant voltage here with one low input. With both low, I get clean 0 volts. In this case, I get a clean 0, and in the high case I get about 4 volts. But this situation is a bit weird because I should have a low output, but instead I have a middle output. This LED is off only because 2.1 volts is not enough to power a blue LED, but if it was red, you can see now that this is dimly lit. Not as brightly lit as when I get a proper high, but this doesn't look right. Now let's analyze this. If I measure the emitter of the gate, this is around 2 volts. And these 2 volts are not coming from the top transistor. I can even disconnect that one. The collector still has 2 volts because the transistor is on, and that connects it with the emitter. But this confirms that only the B switch and transistor are the ones that matter. The problem is that in the base I have 2.6 volts which come through the switch. Well, if the current in the emitter is not coming from the collector, there's only one other option. The current must be coming from the base into the emitter. The power from the switch is in fact driving the LED. What I know now is that the base connection is not merely a control signal. The current there can drive the output too. Once again, I was wrong. And I wasn't surprised to be wrong. I built this without barely understanding how a transistor works. I really like to do that, because when I read how it actually should be and why my version doesn't work, I think I learned it better. What did surprise me was that my mistake was more common than I expected. For example, this question in the electronic stack exchange, where someone has come across the same issue in almost the same circuit. The author is asking about the same problem. The second input is turning the output on. I checked other sources and found that the layout for my gate is actually very commonly found. Even Wikipedia, as of today, refers to the circuit as an AND gate. But we have this important output issue. Perhaps I chose the wrong resistor values? They don't seem to be specified in some places. Let's look at even more places. I can see this design is quite popular. Most people seem to use a 10K for the base, and for the pull down I can see mostly going from 1K to 5K. This last one uses 1K for the base and 100K for the pull down, which is very different. But I don't want to just guess the value, I want to understand what's going on. This is a diagram of our current gate. Let's call RB the resistors on the two bases, and let's call RE the resistor that's close to this emitter over here. We're considering the scenario where only B is high, and the current flow is going here, and shouldn't be going here. But apparently there's some current coming out here, and we know it comes from the base, so it's actually going this way. Something important I learned about transistors is that the path from the base to the emitter, which has this arrow that looks like a diode symbol, works exactly like a diode, including the voltage drop of around 0.7 volts. We can even see that in the datasheet for the on status of the transistor. It says that the base emitter saturation voltage, that's the way it's called, it's typically between 0.6 and 1.2 volts. Then I have a path from 5 volts, because B is high, to 0 volts, which drops around 0.7 volts in the transistor. That means that the other 4.3 volts are dropped in the resistors proportionally to their values. The voltage at the output is given by the voltage drop on RE, and we want that to be low. If I have two identical resistors, like I had in my build, each voltage drop will be half those 4.3 volts. And that is a bit more than 2 volts. That's a lot for a low output, and that's lighting up my LED, at least a red one. If I follow the recommendation that I saw in some of these websites about 10K here and 5K here, the output voltage will be about 1/3 of 4.3, because this is 1/3 of the total resistance. That is roughly 1.4 volts. That won't be enough to light up the LED, but it is still more than the saturation voltage of an hypothetical NET gate connected to this output. So another gate will still consider that a high value, and we want this case where A is low to have a low output. That means that the 10K, 5K actually doesn't work. The version with the 10K here and a 1K here will have an output voltage of 1/11th of 4.3 volts, which is around 0.4 volts. According to the datasheet, the saturation will never be below 0.6 volts, so 0.4 volts seems like a safe low voltage. And if B is low, of course the output will be a clean 0 volts. I have rebuilt the gate here, changing these resistors for 10K resistors, and kept this as a 1K. In this case, we can see that the LED output seems okay in all possible cases. Let's measure the real output voltage at this point. Here I have 0, in this case also 0. In the high case I have 3.8 volts, a good high, and for the problematic case I have around 0.4 volts, which is what we predicted. What about those 0.4 volts? Is that a serious error? Let's measure how the gate is doing overall. We start at 5 volts. The loss on the resistor seems to be almost 4 volts, which is what we wanted. Then we already measure 0.4 volts here. Let's now measure the case with a high output. The loss on the resistor seems to be going from 5 to above 4.5 volts, so about 0.4 volts. Then from the base at 455 to the emitter, I get 3.9, so I've lost between 0.6 or 0.7 volts, which is expected. And the end of the path is at a reference 0 volts. Going back to the output point, we have 3.94, which is a significant loss from the initial voltage, more than 1 volt. My concern now is, when everything is high, will this loss be cumulative and degrade my signal like when we built the gate out of diodes? I could do lots of maths, but perhaps it's easier to build a measure. I have here a couple of pre-built extra gates. I want to try to build something like this, where I chain 3 AND gates together. Now we have our A and B, and that goes to the input of the second gate, which is A and B. I omitted the AND to make it shorter. And that's tied into C, which is currently high. And the output of that goes to this input, ABC, which together with D, which is tied high, should be high at the end. So let's plug this to the output, and we can see that this, again, is not lighting up as expected. And if we measure what's the actual output here, we can see that, well, it's around 2.3 volts, which is not enough for this blue LED. If it was a red LED, as usual, they require less voltage. So we can see a mild signal, but it's not very bright at this moment. And that's because 2.3 volts is again kind of in the middle between high and low. So it's not a very strong output. And we can measure actually what's happening with the voltage as I go through each gate. The first gate has a 4 volt output. Remember we started at almost 5. And then it goes into the second gate, and at the output of the second gate, I got 3.2 volts. And then after another gate, I get 2.3 volts. So there's a successive loss of voltage after each one of the gates. Once again, we can see that transistors are not switches. In particular, an important aspect of NPN bipolar junction transistors is that the connection between the base and the emitter works exactly like a diode. If you just connected the base and the emitter pins of an NPN transistor into a circuit, it will be hard to distinguish it from a regular diode with the anode at the base and the cathode at the emitter. So this includes this voltage drop that we experience across any of these transistors. We can see that from the base, 3.8, to the corresponding emitter, 3.1, I'm losing about 0.7 volts. So essentially, if we follow the path from one of these buttons across all of these transistor and output and transistor and output and transistor and output, I have a chain of diodes, which is the voltage drop that we experience. We actually saw this in the datasheet when we were looking at the voltage drop over here. There's also a mild voltage drop when going from the collector to the emitter. It's typically much smaller, so you see the maximum is 0.3 volts. So all in all, what we have here is that this chain of diodes will degrade the signal. So this gate won't cut it. It has failed our test. So what have we learned? Well, we learned to not believe any design you find on the web. Some of them were obviously untested and would never have worked properly. Some of them were missing details which were actually critical to getting the right results. And even the ones that get the right result don't really work to build practical circuits where you compose the gates. So it's really important to build, measure, and test. I'm not showing it here, but simulation is also quite helpful to understand why things work or why they don't. Let's talk about what's next then. We will try a slightly different approach using transistors that I saw recommended in other places. Perhaps that one will be the one that works. Even if it doesn't, I'll learn something on the way. Thank you for watching, and I'll see you on the next one.